Here are your notes on circuits and Ohm's law, and there's a handout that goes with these notes that you can print out and write on, or you can just write them in your notebook. So electrons, we know they want to move from high to low voltage, and can we use that fact to make them do tricks along the way? And so you need a way to make the voltage. Batteries make a voltage, capacitors will store a voltage until you discharge them, and then they won't have a voltage difference anymore. Or generators will also generate a current and can be used to generate a voltage also. And then you need something for the electrons to run on that's conductive, and that would be wires. So a circuit is a network of conductors where there's a potential difference, a voltage difference, provided by some kind of power source like a battery. So here's a battery, and then wires, and then something along the way that they do. It could be light a bulb, or it could be run a toaster, or it could be run a motor, etc. And then it's that potential difference that pushes the electrons from high to low voltage. So here's a pretty complex circuit. This has a bunch of, maybe you can see these are capacitors here, these little cans. And then it's got these chips that have lots of amazingly small transistors and capacitors inside, and other components that allow them to usually do a lot of digital logic decisions. This is not the same circuit, but here's a drawing of a typical circuit drawing showing the wires connecting different components and the order of that things are connected. But a basic circuit just needs to have some kind of a power source and a closed loop. It's always got to be a closed loop, and there can be branches, but it has to be closed, otherwise the electrons won't feel a push to go from the high voltage to the low voltage. Let's make an analogy with water pipes. So if you have water at high pressure, because it's got a higher height there, this water is at a higher pressure, it's going to flow to a region of lower pressure, and these are going to level out. And that's the idea. You can make another kind of water analogy with pipes. You can say, well, here's a pump that's pumping the water up. Maybe you could pump it up a hill or just pump it up to higher pressure. Water often, especially in really flat places, the water is stored in tanks up off the ground, so it's pumped up there, so it's kept at high pressure. That would be the high pressure part of the pipe. And then this valve is a way to open and close the connection there. And then the water goes through the line, and if the line is narrow like this, that's going to slow down the flow. So that's an analogy to this circuit here, where the battery pumps the current up to pumps the electrons up to a high potential. So this is a high potential, low potential, and this high potential here is connected to a switch. When the switch is closed, the circuit is a complete circle, and then the current will flow through this resistor, which limits how much current can flow, just like this narrow pipe limits how much water can flow. And that's a pretty good way to think about it. It's good to have analogies for circuits. So there are three important things we're talking about with circuits. One is the voltage at any point. It's going to be highest at the high voltage end of the battery and lowest at the low voltage end of the battery, but it's going to be decreasing along the circuit. And then the current, which is the charge per second at any cross section of wire. And if you think about it as water flowing, you actually know that the water flowing here in this part is the same amount of water that's flowing through here, and it's the same amount of water as long as you have one loop. There's nowhere else for the water to go, so the flow rate at any point is the same, but the resistance in this narrow hose is going to slow down the flow everywhere. And same thing here, the resistance of this resistor is going to slow down the current everywhere. And I haven't even told you what a resistor is, but let's say it's something. It could be a light bulb, it could be a thin piece of wire that doesn't let current flow very easily, or it could be an actual resistor, which is a device that's used to slow down current. So voltage is measured in volts. Current is measured in amps or amperes. or coulombs per second. It's charge per time. And current is always the same on a continuous path, but it can split if you have a junction. And then there's resistance, and that's measured in ohms. And it relates voltage and current, and we'll talk about that. Okay, so the current always flows from high voltage to low voltage, but what we're talking about there is positive current flow. So, or conventional current. We're very rarely will you talk about the direction the electrons are flowing. I know it's kind of strange, but this is left over from Benjamin Franklin not knowing about electrons and just making a decision of what was plus and what was minus. But we always talk about current flowing from the plus, from the high voltage to the low voltage. And that current we're talking about is positive charges, which don't actually flow. The conventional current is flowing in the opposite direction that electrons are actually flowing. Okay, Ohm's law relates the current, the voltage, and the resistance, and it's an equation. V equals IR. I is current, V is voltage, R is resistance. And it's a way to describe a lot of basic behavior of circuits, because you can determine the current from the voltage if you know the resistance, or vice versa. And one way to think about this is if you have a higher resistance, like say there's a clog in your sink or in your plumbing, then more resistance, if you have the same voltage, like it's the same battery, it's not changing, you're going to have, if more resistance, you're going to have less current to have that same voltage. And you could rearrange this I equals V over R, or R equals V over I, or different ways so that you can think about what happens if you change one of these and hold the other one fixed. For your lab, you're going to use this PhET simulation, and I'll give you the link in the lab instructions. It has different components, light bulbs, wires, batteries. It has resistors as well. You can even change the value of the resistor, and you notice the color is changing there. We'll talk about that. And you can connect things together and see what happens. See if you can get a bulb to light. You also have a voltmeter that will measure a voltage difference, and you can move these around, connect them to different places. And you also have a current meter which connects at one place in the wire, because it's just measuring the current in that wire. So I actually stopped by the classroom today to show you a real little circuit, just so that it's not all virtual. This is a little bulb and batteries, and you can connect to the bulb and see it light, right? Or you could connect to a little motor and see that run. I'll connect it again. Okay. Or you could connect to a resistor and not see anything at all, but you could measure and see what the current is flowing through this circuit with that kind of a resistance. Your circuit lab will have the first section. It's called circuit exploration, and what I want you to do for that is to explore different things using the PhET simulator. Build some different circuits, make some observations about the circuits, some things you wonder, a diagram of an interesting circuit, and then maybe ask yourself some questions and see what you notice. Like, what if you have 2 light bulbs instead of 1? You can tell brightness and dimness in the PhET simulator. You'll notice that by how many rays come off from the light bulb. Does the order of the parts matter is another kind of question to ask, and then try it. Okay, so let's do a little practice with Ohm's law. It's pretty straightforward. Why don't you try these 2 and pause your video right now? Okay, now I'm telling you the answers. The first one is 0.5 amperes, and the second one is 210 volts. And these are written on your handout, so you can just write your answer right there. These are the symbols we use when we draw real circuit diagrams. A wire, a switch, a resistor, a single cell battery or multiple cell battery. Either one of these is fine for a battery. An ammeter measures current and a voltmeter measures voltage. A light bulb, and you'll see kind of variations on some of these, but that's the basic idea. Here's a little drawing of the circuit I just made with the light bulb. This is the battery, and this is the positive side and the negative sign. Sometimes you'll see a little plus and a little minus, and there's the light bulb. Okay, my symbol doesn't look exactly like what I just showed you. So every circuit needs to be a circle. That's actually what circuit means, right? Circle. But some things can be combined in series or in parallel. Let me show you what that looks like. Okay, so here's a circuit with two resistors, and they're in series because if you go along the path of the circle, they're one after the other. Doesn't matter, I could put one here and here, or one here and one here, or one here and one here, or one here and one here, but as long as they're one after the other in the path, that's series. Here are two resistors in parallel, and you can see that as I go along the path splits in two different directions, so electrons going along here have to choose. They either go this way or they go this way. Whereas on the series, they go through one and then the same electron goes through the next one. This one, the current splits. You could have two different amounts of current in the two resistors, and you will if they're not the same resistance. And then it comes back together at the bottom and goes back to the battery. So it's still a circle, but there's a split in it. That's a parallel. And one thing to know about current meters or ammeters and voltage meters or voltmeters, that ammeters are always wired in series. So that's why when you use the FET simulation, you'll see it's in the wire, along the wire, it's connected. Whereas the voltmeter is wired in parallel. So if you want to know the voltage drop, let me show you that actually. Okay, my voltmeter has two connections. And these two connections, if I want to know the voltage drop from here to here, I put them like this. That's in parallel with that resistor. Or from here to here, I put them like this. Or if I want to know the whole voltage drop, I could go from here to here, or from here to here. It's the same. There's no voltage drop on a wire. So that's how you'll use the ammeter and voltmeter virtually in the FET lab. All right, and finally, you need to know about these resistor colors. Let me give you an example. This is on the back of your handout. So here's the example resistor. The first color is brown, and brown is 1, so that's 1. The second color is black. Black is 0, so 1, 0. And then the third color tells you the multiplier. So orange is times 10 to the third. So 1, 0 times 10 to the third, or 1,000, is 10,000 ohms. And that's the resistance of this resistor. This just tells you this last color, which is either usually gold or silver, tells you how accurate the resistor is. So is it within 5%, 10%? Because it's not going to be exactly 10,000 ohms. That would be too expensive. So it's close and close enough. And engineers pay for the accuracy if they really need it. So now try these three, see if you can figure out what the resistance of each of these is, and pause your video right now. Okay, check your answers. The yellow, violet, red is 4,700 ohms, or 4,700, or 4.7 thousand, same thing. The brown, black, green is 1 with, how many zeros? 1, 2, 3, 4. 1 with 6 zeros, so 1 mega ohm. And the green, blue, red is 5,600 or 5,600 ohms. Okay, it's time for you to do the lab. You're going to be building various circuits. The instructions are there posted for you. You're going to be working with light bulbs and resistors, and you're also going to be looking at resistors in series and noticing how that affects the voltage and the overall current. And you're going to be looking at Ohm's law with all of those things. Ohm's law applies not only to the whole circuit, but to one resistor. The voltage, current, and resistance of that one resistor will agree with Ohm's law.